Hello everyone! Have you ever wondered how your favorite apps instantly recognize and translate languages from all around the world? Today we're diving into the magic behind it, building our very own language detection machine learning model from scratch. Ready to unlock the secrets of multilingual text processing? Let's get started! Importing libraries. In this code, several libraries are imported to facilitate data manipulation, visualization, machine learning, and model evaluation. Pandas is used for data manipulation and analysis, providing data structures such as data frames to handle structured data efficiently. NumPy supports large multidimensional arrays and matrices, along with a collection of mathematical functions to operate on these arrays. Regular expressions are used for text processing and cleaning. Seaborn and Matplotlib are powerful visualization libraries. Seaborn builds on Matplotlib to provide a high-level interface for drawing attractive statistical graphics. Pickle is used for serializing and deserializing Python objects, allowing models and data to be saved and loaded later. Scikit-learn provides simple and efficient tools for data mining and data analysis, including modules for feature extraction TF-IDF vectorizer, model selection train test split, GridSearchCV, machine learning algorithms MultinomialNB, performance metrics accuracy score, confusion matrix, classification report, and creating machine learning pipelines pipeline. LabelEncoder is used for encoding categorical labels into numerical values. Warnings module is used to suppress any unnecessary warnings that might clutter the output. Data preprocessing. Loading the dataset. Load the dataset from a CSV file and display the first few rows to inspect the data. Check for any missing values in the dataset. Visualizing the distribution of languages. Plot the distribution of different languages in the dataset to understand the dataset's composition. Extracting features and labels. Separate the dataset into features, text, and labels language. Encoding labels. Encode the categorical language labels into numerical values using LabelEncoder. Example: suppose we have a list of languages. The fit transform method performs two tasks. Fit: it learns the unique labels in the data and assigns each a unique integer. Transform: it converts each label to its corresponding integer. For our example, the LabelEncoder will assign English to 0, French to 1, Spanish to 2. Therefore, encoded labels will be text cleaning. Define a function to clean the text data by removing special characters and converting it to lowercase. Apply this function to all text data in the feature set. Feature engineering. Train test split. Split the data into training and testing sets with 80% training data and 20% testing data. Using TF-IDF Vectorizer. Use TF-IDF Vectorizer to convert text data into numerical features. It considers unigrams and bigrams to capture more context. Unigrams and bigrams. Unigrams, single words. I love machine learning is fun. Bigrams, pairs of consecutive words. I love machine learning. Learning is fun. TF-IDF calculation. Term frequency, number of times a word, or n-gram, appears in a document. Inverse document frequency, measure of how common or rare a word, or n-gram, is across all documents. Common words get lower weights. Example, suppose we have a list of text documents, sentences. After fitting, the vectorizer creates a vocabulary of unigrams and bigrams. TF-IDF matrix. The matrix shows the TF-IDF score of each n-gram in each document. Fit the vectorizer on the training data and transform both the training and testing data. Model selection and hyperparameter tuning. Multinomial Naive Bayes with hyperparameter tuning. This initializes the Multinomial Naive Bayes classifier, which is suitable for classification with discrete features like word counts in text classification. We define the range of hyperparameters we want to test. Alpha is a smoothing parameter in Naive Bayes. Smaller values mean less smoothing, while larger values mean more smoothing. GridSearchCV is used to perform hyperparameter tuning. CV equals 5 specifies 5-fold cross-validation, meaning the training data is split into 5 parts. The model is trained on 4 parts and validated on the 5th part, rotating through all parts. Scoring equals accuracy means we evaluate models based on their accuracy. Fit operation performs the grid search, fitting the model multiple times with different values of alpha, each time using cross-validation to evaluate performance. Grid Search Best Estimator retrieves the model with the best performance, that is highest accuracy, from the grid search. Visualizations. Plotting accuracy over different alpha values. Visualize the model accuracy over different values of the hyperparameter alpha to identify the optimal value. Model validation. Making predictions and evaluating the model. Use the best model to make predictions on the test data. Evaluate the model using accuracy score, confusion matrix, and classification report to understand its performance. The classification report function from Scikit-learn metrics provides a detailed summary of the performance of a classification model. The report includes several key metrics for each class, as well as overall metrics. For each class languages, 0 to 16 in our example, we have the following metrics. Precision. How many of the predictions for this class were correct? Recall. How many of the actual instances of this class were correctly predicted? F1 score. The harmonic mean of precision and recall for this class. Support. The number of actual instances of the class in the test data. For example, for class 0, precision 1.00, 100% of the predicted instances of class 0 were correct. Recall 0.98, 98% of the actual instances of class 0 were correctly predicted. F1 score 0.99, the balance between precision and recall. Support 96, there were 96 actual instances of class 0 in the test data. Visualizing the confusion matrix. Plot a heat map of the confusion matrix to visualize how well the model's predictions match the actual labels. Model deployment. Creating and saving the pipeline. Create a pipeline that includes the TF-IDF vectorizer and the best naive Bayes model. Fit the pipeline on the training data. Save the trained pipeline to a file using Pickle for future use. Making predictions. Making predictions with the pipeline. Use the saved pipeline to make predictions on new text data. The predictions are displayed along with the corresponding language. Building a robust and accurate language detection model involves several key steps. First, the data is preprocessed by loading and cleaning the dataset to ensure it is suitable for analysis. Feature engineering is then applied, converting the text data into numerical features using the TF-IDF vectorizer. The model selection process follows, where the Multinomial Naive Bayes algorithm is chosen and its hyperparameters are fine-tuned for optimal performance. The model is then trained on the training data. Model validation is conducted by evaluating the trained model's performance on the test data through accuracy scores, confusion matrices, and classification reports. For deployment, the trained model and vectorizer are packaged into a pipeline and saved for future use. Finally, the pipeline is employed to predict languages for new text data, demonstrating the practical application of the language detection model. These steps together form a comprehensive approach to building an effective language detection system. Find the dataset and code in the description below. I trust you found this video helpful. Thank you.